Hello, students of science. In this video, we're going to talk about the reaction rate of chemicals. Here you can see some of them are being converted into different chemicals. We're going to talk about factors that will affect that. So in this reaction here in this beaker, we start off with all of one purple chemical, and we can see that over time, the amount of the purple chemical is going to drop all the way down to 0, and the amount of the green chemical is going to increase all the way up until it's going to reach 100% of them. Here we can see how it's being converted inside the beaker. We're going to talk about things that affect that reaction rate. So the reaction rate is essentially what determines how fast a reaction goes. So it's not just does it go all the way to completion, but how quickly does that happen to go here. Here we start with all red, then it becomes partial red, partial blue, and then mostly blue. So this is 20 seconds, 40 seconds. We're going to talk about things that affect that. So some factors that can affect the nature of the reactants, the surface area, the temperature, the concentration, and the presence of catalysts. Don't copy this down right now. We're going to have a section on each one of these. But these are all different things that will affect how quickly it turns from one into the other. So let's first talk about the nature of reactants. Different reactants, different things that I start with, are going to have different reactions. Here I have hydrogen plus chlorine gas that is going to create hydrogen chloride. Well, here's another one. Hydrogen plus nitrogen is going to create ammonia. Now you'll see both of these have hydrogen. However, this first one is going to be a very fast, very energetic reaction, where this one is going to be a slow reaction. Even though they both have hydrogen in it, this chlorine here or this nitrogen here, that's going to affect it. So the nature of that is going to affect how quickly this reaction happens. Oxygen plus sodium, that's going to create sodium oxide. Oxygen plus iron is going to create iron 3 oxide. Both of them have oxygen in here. However, this first one, a fast energetic reaction, whereas the second one, a much slower reaction. So the other thing that it's reacting with is very important for determining how quickly that's going to react. In your notes, just copy down one of these. Surface area. Surface area is very important as well. An increase in surface area is an increase how quickly that reaction happens to go. If we have something that's in like a powdered form, which has the same volume as it would be in like lumps or whatnot there, however, it's going to have much quicker surface area, that is going to react and make my total amount much quicker than those smaller lumps are going to actually get to there. Think of it as like burning a wood log versus burning wood chips. Wood chips are going to burn much more quickly and more vigorously because a lot more surface area is exposed to the heat. Logs, they can only burn as quickly as the outside is actually exposed. Here I have two different compounds reacting on a substrate. Here on this flat one here, I'm able to fit in 8 of those molecules, whereas this one, which has more surface area because of those bends and contours and whatnot, I'm able to get not only those original 8, but 3 more as well, just by an increase of the surface area. So more of it is going to be able to be in contact between my two reactants that are actually happening there. Gases have the most surface area since they're all diffuse and in the air. Those are the ones that usually react the fastest. Here would be something that's in solid, here would be something that's in liquid, and in gas, you're just going to have those individual particles. Very quick reaction because a lot of surface area is exposed. When we're talking about something like a heterogeneous reaction, that is something that has reactants in different phases, like a solid, a liquid, or a gas, where one's solid, where one's liquid. We talked about homogeneous before. This would be heterogeneous. Something's in liquid, something's in solid. And only the stuff that's exposed to the outside can actually react. So the more of that there is, the quicker reaction we have. Temperature. Temperature also has a very large effect on this. Higher temperatures are going to mean more kinetic energy. More kinetic energy, more movement for particles in a fast reaction. At a cold temperature, they're moving kind of slow. Hot temperature, much more quickly. When something's moving quicker, we're going to have more collisions and more collisions with enough energy to react. Remember, with collision theory, they need to combine and they need to combine with enough energy. Increasing the temperature means you're increasing the average kinetic energy of all of those particles. So eventually, both of these reactions at 100 degrees Celsius or 75 will reach the full amount. However, at 100 degrees Celsius, it will reach that much more quickly. When we decrease in temperature, that of course is going to result in a decrease in the reaction rate as well. So as temperature goes up, so does reaction rate. As temperature goes down, so does reaction rate. If that temperature drops below the activation energy, let's say 300 Kelvin is where it's at and anything below it won't happen, the reaction is not going to happen. So some chemical reactions need to have a minimum temperature. Otherwise, those particles are not going to collide with enough energy, cannot overcome the activation energy, and the reaction is not going to happen. The higher the concentration of reactants, the higher the reaction rate. This kind of makes sense. Not a lot of molecules here, not a lot of reactions. Increase the concentration, and suddenly we've got a lot more collisions, a lot more things that can possibly result in our products. So the greater number of collisions we have, the greater number of reactions we're going to see. Low concentration, just a few collisions. Higher concentration, a lot more collisions. So right now here we can see one example of a collision. If I was to increase this concentration here, where you see a whole bunch more, we would have a much faster reaction rate. We'd have a lot more products made a lot more quickly. Finally, the presence of a catalyst. A catalyst is anything that speeds up a reaction without actually being used up or changed in the reaction. Enzymes are a good example of a biological catalyst. So here I am going from my reactants to the products, and I have to overcome that activation energy. If you add in a catalyst, though, you can see that this activation energy is going to be less. Before we had the uncatalyzed pathway, here we are with the catalyzed pathway. It's a lot easier to get down to my products because the activation energy is lower. So again, here's my activated complex with a catalyst. It's easier to overcome that in this particular endothermic reaction. A catalyst makes that happen. Think of it as like trying to push something up and over that hill. Without a catalyst, you'd have to go up the full hill. With a catalyst, you kind of cut the top off the hill there. It's going to go a lot quicker and a lot easier. And let's say the temperature, if you almost imagine like a horizontal line here is the temperature. At this particular temperature, let's say we're at like 5, the catalyzed reaction would be the only one that takes place because there's not enough energy to get up and over that particular hill. So catalyst lowers the activation energy. Some of them help by just orienting the reactants in the correct direction. We have an enzyme and we're trying to make this product right here. An enzyme just facilitates that by making sure that they're lined up correctly. Some catalysts are then reformed later, so you can have something that's consumed and then made again later on in the reaction. If in the fact that it's not used up in the reaction overall, if at the end you start with it the same way you ended with it, that's going to be a catalyst. It's not actually used up. And sometimes you can get enzyme inhibitors. Enzyme inhibitors are going to slow down the rate of reaction, sometimes by just essentially sticking in there. So here we have an inhibitor that's going to go inside the active site of the enzyme. Now my substrates, my reactants, can't actually go in there and I can't make products. So inhibitors can slow this reaction down. Here we can see I have a potential energy diagram. Here's my change in enthalpy. So here's my reactants, here's my products. The change in enthalpy in this particular exothermic reaction is represented here. Catalyzed versus uncatalyzed, it doesn't matter. They're going to end up the exact same way. The difference is with my active complex, my activation energy is going to be a lot higher. So my uncatalyzed reaction versus my catalyzed reaction. Now you'll notice that my catalyzed reaction has a couple different kind of bumps here. That's because each and every one of these steps right here, we can see the blue one binds and then the red one binds and then they together bind. Each one of those is going to be represented by its own little peak on here, its own transitional state. But so all of these different parts here, these are going to be called their chemical intermediates. They don't appear in the overall equation. My enzyme is regenerated at the end without actually being used up. So that's the whole idea behind catalysts. They're going to make it easier to get from here to there, and they're not going to be used up in the reaction. It doesn't change your enthalpy. It doesn't change where you start with or what you end with. It just makes it a lot easier and a lot quicker to get there. And sometimes we have these multiple intermediate transitional stages with a catalyzed reaction. Finally, the rate determining step. The slowest step in any reaction mechanism is going to be the rate determining step. Think of it as like filtering sand through this weird little hourglass there. The one that's going to limit how quickly sand can make it to the bottom, that's going to be the narrowest one. We would say that this is the rate determining step of this reaction because it's the narrowest. Here we have another one. Imagine we're trying to fill up this bottom Erlenmeyer flask right there from my beaker up there, and I cannot overfill any funnel. Well, I'm going to be limited in how much I can pour in there by the size of the smallest funnel. It doesn't matter if it's the first, second, or third step. I am limited by that one. We would call that my rate determining step. Here I have a chemical reaction. I'm going from A and B eventually to ABC. And so we've got two different steps here. A plus B makes AB. So that's this first one right here. And then AB plus C is going to make ABC. So this one is going to be my slow reaction because this one has the highest activation energy. That one slows me down the most. That is going to be represented by the highest peak on my potential energy diagram. My second one is going to be a much quicker one. If I got the energy to make it up and over that one, I probably have the energy to make it up and over that one. So this one happens slowly, this one happens quickly. I am limited by this one, but not by that one.